Hello, my Algebra 2 students. We are doing sinusoidal modeling, which is just fun to say. So the first little blank here says, the sine and cosine functions can be used to model various real-world phenomena that are sinusoidal or cyclic is essentially what that means. Something that follows a cycle, it keeps going, all right? Repeating in regular intervals. So we can build it to create the equations in sine or cosine. You know all these little details already, so I'm going to skip past that, but feel free to reference them as you need them. And it says, since we choose where to start, a sine curve is arbitrary since it keeps going. It's easier if we make the phase shift equal to 0. So we're going to try to avoid having to deal with the phase shift for the most part, all right? So the first one is talking about tides. So it says the tides in a particular bay can be modeled with an equation in the form of D equals A times cosine of BT plus C, all right? T is representing the number of hours since high tide, so that's important. So down at the bottom of the graph, that's going to be hours since high tide. D represents the depth of the water in the bay. All right, so over here, this will be like in feet. That's the depth. The maximum depth of the water is 36 feet. The minimum depth is 22 feet. So right there kind of tells us the scale we need on the y-axis. So over here, we can say like 22 up to 36. And don't worry about it being perfectly spaced. It's not a big deal. Right? It does say that high tide is every 12 hours. So since it's the number of hours since high tide, we'd want to start at a high tide. So start the water as deep as possible. And then we're going to finish at 12 hours. Now, before I get too far into it, it does say over here, sketch a graph for the scenario for 2 full periods. So normally I would say that we just need to go to 12, but we have to go to 2 periods. So we're going to go to 24. So high tide here at the 12-hour mark, and then again at the 24-hour mark. All right, so those are high tides, like this and this. All right, that says label the axes and the points in the curve that represent the high and the low tide. So low tide has to be happening at the halfway mark then. So at 6, hitting that low value of 22. At 18, hitting that low value of 22 again. All right. To figure out the rest of the details, you kind of need to know like what's going on in between. So we know it'll scoop down and back up, but I want to be a little more exact. So to figure out what the A, B, and C are, amplitude, frequency, and then this is the midline. I actually want to start with the midline. So if you can think to yesterday's notes, you can calculate the midline by averaging the maximum and the minimum values that the graph will hit. So if we do 22 plus 36 and divide it by 2, that'll give us 58 over 2, or 29. So on your graph, do your best to plot the middle of that, and then go ahead and draw that in as a horizontal line, because that would be y equals 29 right there. That was weird. It just asked me if I wanted to stay in the call. Yes, I do. All right, so the halfway points between 0 and 6. So like 3, between 6 and 12, so that would be 9. That's when it hits the midline. So halfway, that would be 15. Halfway, that would be 21. Go ahead and plot those points. Then you can fully connect. All right, so I want it to be as exact as possible, meaning that every cycle I want to see those exact 5 points plotted. All right, now we can pick out the amplitude. And so that's going to be the difference from the midline to the top or midline to the bottom. So just subtract. So I can do 36 minus 29 or 29 minus 22. Either way, you're going to get 7. So there's your amplitude there. Right? And then the last part, the frequency. Now, in this case, since I'm not scaling it from 0 to 2 pi, you really have to figure out the period first. So the period, or the length of one cycle, is 12. So if the period's 12, set that equal to 2 pi over b and then solve. So if I throw that over 1 and cross multiply, I get 12b equals 2 pi, and then divide by 12. So b comes out to be pi over 6. So now I have all the details that I need to write the equation of the graph. I'm going to write the equation over here because I actually have some space over here. And that's going to be y equals, fill in your A, So 7, and then cosine of, fill in the b, pi over 6 t, and then plus that midline of 29. All right, that's the equation that we just came up with right here. All right, for the second part of this question, I'm going to tip this up a little bit. It's saying tinker boats cannot be in the bay when the depth of the water is less, or should say less than or equal to 25 feet. Basically, because it's going to hit the bottom, and that would not be good. Set up an inequality and solve it graphically to determine all points in time on the interval from 0 to 24 when tankers can't be in the bay. All right, so what we're looking at is they can't be in the bay when the water, so like the depth of the water, is less than or equal to 25 feet. Right? So now graphically, if we come on up here, 25 would be about here, let's say. And so if I kind of draw in, I'm going to pick a different color. I'll use my red pen here. If I draw in 25, we're looking at what is the time frame from here to here, because that's when the tanker can't be in the bay. And what's the time frame from here to here, because that's when it can't be in the bay. All right, now I can sort of approximate maybe and say like somewhere between 4 and like 7 hours, but we want to be a little bit more exact. And so to be able to do that, this is where we can use the calculator. Into y1, we're going to put the equation we came up with. So 7 times the cosine of pi over 6 t plus 29. And into y2, we can put 25. Because what we're actually solving for is when this is less than or equal to 25. We want to figure out when that's occurring. So if we can figure out where they intersect, we can see the little gaps at where that's going to happen. All right, so into my y equals, let me get rid of anything that's in there that I don't need. And I'm going to set in there 7. Excuse me, let me slide it so maybe you guys can see it. There we go. So 7 and then times the cosine of pi over 6 and then t, or x in this case, plus 29. Right? Now I need to change my mode to make sure I'm in radians. Good. And my window. I'm going to set my window to match this right here. So the x value goes from 0 to 24. Scaling, I'll do every 3 tick mark, or every 3, because that's how I have my tick marks here. And then for my y scaling, I really need to see from like 0 up to at least 36. So maybe I'll make it like 40. Okay, and then I'll graph. So there's the cosine curve right there, from 0 to 24 hours. And then I forgot, I need to put into y2 the 25. Let me add that in there. Here we go. And so that's that nice red line that we have right here. So I want to look at where the intersection is. So just like any other graph, second, trace, intersect is what we need to do here. So if I go second, trace, intersect, I'm going to get close to that first one. I'll work left to right. First curve, second curve, take a guess. It's coming out to be that first time, so the nearest 1/10 of an hour is about 4.2 hours after high tide. So that's that first value. So right here would be about 4.2. And then the second value, second trace intersect, shimmy it on over here, and then enter, enter, enter. That's happening at about 7.8 hours. Right? And then because that cycle repeats, I can either slide on over and calculate those two, or I can remind myself it repeats every 12 hours. So I can simply just add 12 hours to this answer and add 12 hours to that answer. So it also happened at 16.2 hours after that first high tide and at 19.8 hours after that first high tide. So that would be the times between here and here and between here and here when that tanker can't be in the bay. Okay, flip it on over to the back. So on to page 13. Try to refocus that. Hopefully that'll help a little bit. There we go. On page 13, we're going to do some of this together, some we'll save for class. So we're going to do the first one, the height of the yo-yo. saying above the ground can be modeled using this equation. So instead of us creating the equation, it's given this time. H represents the height of the yo-yo in feet above ground. T represents the time in seconds since the yo-yos first dropped. So, from the maximum height. So it's going to start up here and like drop down and come back up and drop down and come back up. So you get the deal. It says determine the maximum minimum heights that the yo-yo reaches above the ground. So essentially, you're being asked for the range. So when we think about range, amplitude should come to mind. But because the midline is something other than zero, we can't just say that it goes, from negative to positive of the amplitude. We have to think about the midline, and then we want to go up and down whatever the amplitude value is. So the midline here would be the 2.25. And then we're going to increase and decrease the amplitude of 1.75. And so if you subtract those two, you're going to end up with 0.5. If you add them, you're going to end up with 4. And so the maximum and minimum heights would be 0.5 feet. Oops. So the minimum, or maybe 0.5 might be easier. And then the maximum would be 4 feet. Cool. How much time does it take for the yo-yo to return to the maximum height the first time? So it says that it's starting at the maximum height, and it's a cosine graph, so it drops down, and then it comes back up. If they're asking how much time has elapsed, what they're really asking is what is the period of the graph, because that's the length of that cycle. So if we do 2 pi over b, that'll get us our answer. So in this case, that would be 2 pi over, that's the b value of pi, and it would be 2. And so time, they're saying, is in seconds. So this would be 2 seconds that it takes when you drop the yo-yo for it to come back up to the top. All right, example 3, we're actually going to save this guy for class. I think it's important that we walk through one of these together in person. Let's do the very last one together. So example 4, it's saying the possible hours of daylight in a given day is a function of the day of the year. So we know like it's later in the summer, darker in the winter. So in Poughkeepsie, New York, the minimum hours of daylight occurring on the winter solstice is 9 hours. The maximum hours of daylight on the summer solstice is equal to 15 hours. If the hours of daylight can be modeled using a sinusoidal equation, so that means sine or cosine, what's the equation's amplitude? All right, what I would want you to think of is, let's draw a baby little sketch to see what's going on. So they're saying at the winter solstice, it's as low as 9 hours a day. Summer solstice, it goes up to 15 hours a day, right? So it does something like this, and goes up and comes back down kind of thing, right? If the hours of daylight are modeled by this, what's the equation's amplitude? Well, the amplitude is the distance from the midline to the top or the midline to the bottom. So first things first, find the midline. So the midline is the average of the min and the max. So if I add those together, that's going to give me 24 over 2 or 12, which makes sense. That would go right through the middle. And now the amplitude is that little distance right there. So the amplitude would be the difference from 15 to 12 or from 12 to 9. But either way, you'll get that same answer. That would be the amplitude of 3. All right, get ready to do that missing question tomorrow. See you guys then.